Shortly after midnight on March 8, 2014, Malaysia Airlines Flight MH370 departed Kuala Lumpur International Airport for what should have been a routine overnight flight to Beijing, China. It never arrived. Sometime after 1 a.m., when the plane was over the South China Sea, it stopped communicating with air traffic controllers and disappeared from radar. What happened next is a topic of intense discussion and debate. At first, it was thought that the plane had crashed near where it had lost contact, but military primary radar and satellite data showed that the plane had instead turned back to Malaysia. But rather than land, it continued out to sea and eventually to the South Indian Ocean, where it presumably crashed. The big question is, why? Many theories have been proposed, and some have been defended with vigor, but these are all based on circumstantial evidence and copious amounts of speculation. I hope to show that almost all of these theories are wrong and that the available data support one and only one conclusion. Now, I do acknowledge that no one can say definitively that this conclusion is correct. Only those who were on board at the time could do so, and they are no longer with us. But it is the only conclusion that is consistent with all the available data and information. First, there is the ever-present possibility that one of the pilots hijacked his own plane. While there are several examples in aviation history of pilots who deliberately sent their planes crashing into the ground or sea, it is difficult to find an example of one who hijacked a plane and first flew it for hours to the point of fuel exhaustion. The closest example that I have been able to find is that of the 1999 Air Botswana incident, where one of the airline's pilots, who had failed 2 physicals and was thus disqualified from flying, stole one of the airline's ATR-42 aircraft, flew it for hours, making numerous exorbitant demands, and then, at the point of fuel exhaustion, crashed it into the remaining planes of the airline, leaving Air Botswana unable to operate. The pilot, by the way, did not survive. However, in the case of MH370, according to the Safety Information Report and the report of the Royal Malaysia Police, neither the captain nor the first officer had any of the medical or behavioral issues of the sort exhibited by the Air Botswana pilot. A popular explanation is that there was a fire in the cargo hold due to the presence of lithium-ion batteries, which were part of the cargo manifest. Fires are rare on aircraft, but when they occur, they can be deadly. South African 295, Swissair 111, and UPS 6 are all examples of flights that had onboard cargo or electrical fires, with the last one being due to lithium-ion batteries in the cargo hold. Just how a fire would cause MH370 to follow the flight path that it did is unclear, but the possibility still needs to be kept open. Another oft-mentioned explanation is hypoxia, oxygen starvation due to loss of pressurization at high altitude. This is the favorite explanation of Christine Negroni, aviation journalist and author of the book The Crash Detectives. Loss of pressurization is not actually an uncommon event. It happens from time to time on commercial flights, but is easily handled by a rapid descent to a safe altitude. However, if not detected, it can lead to loss of consciousness and loss of control of the aircraft. A famous case is that of Helios 522 in 2005, when shortly after takeoff, the pilots misinterpreted warnings of loss of pressurization and continued climbing to a cruising altitude, eventually passing out and leading to the plane flying on autopilot for hours until fuel exhaustion, causing it to crash. In the case of MH370, the theory is that the pilots didn't immediately pass out but became befuddled, which contributed to the bizarre flight path after the turnback. Yet another oft-mentioned explanation is that there was some kind of electrical failure. This was the explanation given by Gregory Keith in a lawsuit that he filed against Boeing regarding MH370, in which he offered the following possible failure modes: defective and inadequately protected wiring near combustible sources like the emergency oxygen supply, a defective transponder, faulty avionics and communication systems in the cockpit. The defects caused and or allowed a massive and cascading sequence of electrical failures on board the lost airplane, which disabled vital systems, making it impossible for the crew to navigate the plane or for the plane to communicate with the ground stations, leaving the aircraft to fly without the ability to communicate or control the aircraft until the plane ran out of fuel. Now, people who are familiar with the electrical systems on board a Boeing 777 are quick to point out that Boeing designed in massive redundancy in those systems, such that a failure of the type needed to create the conditions as described in the lawsuit would be essentially impossible. However, aviation experience does provide a counterexample. In 2018, LATAM Flight 8084, a Boeing 777, suffered a massive electrical failure causing the loss of all electrical power to the aircraft, except for that from the batteries and a device called a RAT, the Ram Air Turbine, intended for use only in the most extreme emergencies. The root cause was a short circuit in a connector, which led to a cascade of circuit and bus breakers opening. Now, the LATAM flight did land successfully, but it blew out all tires and required ground emergency services to extinguish the resulting fire. Then there are a plethora of other explanations for the loss of MH370, some slightly plausible even if unlikely, others rather far-fetched. One person is convinced that an oxygen tank failed in an explosive fashion, taking out one of the Ames equipment cabinets in the main equipment bay and resulting in collateral damage to equipment and depressurization of the plane. Now, that possibility may seem far-fetched, but just such an incident did actually occur in 2008 on Qantas Flight 30. The oxygen tank was part of a system that provided oxygen to the flight crew in the event of a depressurization or other events that degrade air quality on the flight deck. As was presented on a recent Netflix documentary, aviation journalist Jeff Wise theorizes that a Russian or Ukrainian passenger snuck into the electronic equipment bay through a hatchway accessible in the first-class cabin and commandeered the plane from there. Right. Also presented in the Netflix documentary, journalist and author Florence de Changy has postulated that two U.S. AWACS planes somehow cloaked MH370 and blocked all its communications due to AWACS having phenomenal jamming capabilities. The fact that AWACS actually has zero jamming capability is of no consequence. Whatever. So now we come to the one piece of data that cannot be explained by any of the accident scenarios that have been described so far. I call it the smoking gun because it tells us exactly what happened on board MH370 that fateful evening. The smoking gun was first spotted and reported by a user with the handle DCP123 on the forum Professional Pilots Rumor Network a little more than 2 hours after Malaysia Airlines had issued a media statement announcing the loss of the aircraft. Paraphrasing slightly, what this user wrote was, Flight Radar 24, MH370 is at 35,000 on heading 25 until 1719, then it goes to 0 feet. Another user with the handle AAO Petrie noted the same thing on Reddit about 2.5 hours after that. FlightRadar24.com shows 0 alt, 471 knots at last known radar contact. I've highlighted the smoking gun in bold red letters, but in order to understand why it is a smoking gun, I need to digress a bit and discuss the functioning of certain equipment on an aircraft like a Boeing 777 and air navigation in general. During World War II, radar became a highly effective technology to detect and track enemy aircraft. However, it was soon realized that it would be advantageous to not just detect an aircraft, but also to be able to identify whether it was one of ours or one of theirs. As an example, early on December 7, 1941, a radar station on the island of Oahu detected a large number of aircraft approaching the island, but the radar operator was told that there were likely a flight of B-17 bombers that were expected to arrive later that morning. Well, a flight of B-17 bombers did arrive that morning, but these weren't them. Instead, they were Japanese carrier aircraft coming in to drop some bombs and torpedoes on the battleships anchored at Pearl Harbor. This need led to the development of IFF, Identification Friend or Foe. Many variant systems were tried, but all involved installing a device called a transponder on an aircraft that would respond to an interrogating signal from the radar operator and broadcast a unique identifying signal in return. These systems eventually developed into what we call secondary radar today. A transponder on an aircraft responds to an interrogating signal from the radar and responds with the digital pulses encoding the aircraft identity. One capability added to the system early on was the ability for an aircraft to also respond with its altitude, an important piece of information for air traffic controllers that is otherwise difficult to measure using radar alone. Virtually all aircraft around the world today are required to carry a transponder on board. As aircraft became equipped with GPS receivers, transponders were augmented with a system called ADSB, in which an aircraft spontaneously broadcasts its own position, altitude, speed, and direction of travel twice per second. Any other aircraft equipped with an ADSB receiver can pick up these broadcasts and obtain a three-dimensional view of the air traffic in the vicinity. Indeed, one can go one step further and use this information to determine if a collision with another aircraft is imminent, and if so, the system can automatically generate suggested maneuvers for the two aircraft to alleviate the danger. This system, TA/RA, or Traffic Advisory Resolution Advisory, is normally active on all large commercial aircraft. The ADSB broadcasts are non-directional and can be picked up by anyone, including people on the ground. And in fact, that is how flight tracker websites operate. They have a network of volunteers around the world who are provided with receivers to monitor these broadcasts and send them back via internet to the flight tracker website. A low-end receiver is relatively cheap. One can purchase a device called a software-defined radio for maybe $30 from Amazon or other fine merchants. And with the appropriate piece of software, you can even set up your own flight tracker website, albeit just monitoring traffic in your local neighborhood. Now, such a volunteer might be collecting ADSB data from a large number of aircraft, but only have a low bandwidth internet connection. So the way that the collection software works is that while it records all the incoming data, it sends only a small portion back to the flight tracker website. It appears that some massaging of the data is done, interpolating, smoothing, checking for erroneous bits of information, because what the flight tracker website reports doesn't always match exactly with the raw data at any particular time. For example, while monitoring air traffic at one airport, I watched landing aircraft appear to skid off the end of the runway into oncoming traffic on a nearby highway, then miraculously jump back onto the runway as if nothing had happened. So one always needs to be cautious about taking the data reported by one of these websites literally. I'm now going to switch gears and talk briefly about aviation charts. It first helps to think about how you drive long distances in an automobile. You often go from one city to the next along major highways that connect the two together. The equivalents of cities and highways in the aviation world are waypoints and airways, defined not by physical locations, but rather by virtual points and lines drawn on aviation charts. The section of chart shown here gives the original flight plan of MH370 on March 8, 2014. It was planned to first travel along airway R208 from Kuala Lumpur to waypoint IGARI, then make a right turn and head along airway M765 to the next waypoint Bithad, and finally turn left along airway L637 heading towards Beijing. Now, an aircraft traveling at 470 knots cannot spin on a dime, meaning that it cannot instantaneously make a 34-degree turn to the right at the exact moment that it reaches IGARI. Instead, IGARI is called a flyby waypoint, which means that the aircraft will actually fly a bank turn and cut the corner, so to speak, as it passes IGARI. The resulting flight path is shown on the inset figure. One other detail is worth noting. Airspace is divided into flight information regions, each one controlled by an air traffic control center. The operational boundary between two FIRs is defined as the transfer of control point. For MH370, waypoint IGARI was a transfer point between airspace controlled by Kuala Lumpur Air Traffic Control Center and airspace controlled by Ho Chi Minh City Air Traffic Control Center. Pilots have a device with a keypad and a display mounted in the center console called a Control Display Unit, or CDU, that is used to interact with the flight management computer. The device can display a plethora of information, but the only one that is of interest here is called the Active Route Legs page. This page displays progress that the aircraft is making as it travels along a pre-programmed flight plan. The immediate upcoming waypoint is shown in magenta on the top line, and the following waypoints are listed below in white. Once a waypoint is passed, it scrolls off the top of the display, and all the following waypoints move up one line. Thus, as MH370 was approaching IGARI, this page would show IGARI in magenta at the top with Bithad shown in white one line below. After passing IGARI, Bithad would scroll up to the top line, and it would now be displayed in magenta. What defines the point where MH370 is considered to have passed IGARI, given that it was following a curved flyby route and never actually passed over the waypoint itself? Without delving too much into the technical criterion, for the purpose here, it was the point at which IGARI was a beam of the aircraft, that is, the point at which the direction to IGARI was exactly 90 degrees to the direction of travel. A detailed understanding of the exact sequence of events leading up to the disappearance of MH370 has been hampered by the fact that different sources have provided inconsistent details on what was actually recorded. Thus, the Safety Information Report states that at Kuala Lumpur Air Traffic Control Center, quote, the mode S symbol of MH370 dropped from the radar display at 20 minutes 36 seconds after 1 a.m. local time, and the last secondary radar position symbol of MH370 was recorded at 21 minutes 13 seconds, end quote, that is 37 seconds later. However, at Ho Chi Minh Air Traffic Control Center, at 20 minutes 59 seconds, the blip from MH370 from both secondary search radar and ADSB radar position symbols disappeared from the radar display, which means it disappeared 14 seconds earlier at Ho Chi Minh City than it did at Kuala Lumpur. Precisely what caused each of these events to occur or why they occurred at different times is not explained in the report. Of all the flight tracker websites operating at the time, only Flight Radar 24 had a receiver located close enough to MH370 to capture the ADSB broadcasts at the time that it disappeared. The key lines from the track log are shown here in the top panel. Now it turns out that the last line at 17:21:03 is artificial and is likely some extrapolation done by Flight Radar 24, but the others all appear to be valid. The glaring issue is that between 17:19:28 and 17:20:35, the altitude drops from 35,000 feet to 0. This is the anomaly reported previously on the social media forums, but the meaning was unclear at the time. Was it just a case of bad data? Now things get interesting. It turns out that, unbeknownst to anybody at the time, Malaysia was also operating an ADSB station at Terengganu on the northeast coast of Malaysia, close to the flight path of MH370, and it recorded the entire stream of data from the flight. For some reason, the Safety Information Report omitted any mention of its existence. However, in April of 2019, Victor Ianello, who operates the website radiantphysics.com, obtained and posted a complete copy of the ADSB log for MH370. It can be fetched from the link shown here. With this new information, we can finally, for the first time, follow the disappearance of MH370 second by second. The ADSB log contains over 3,500 records starting about 7 minutes after takeoff, so it will not be reproduced here in full. However, this figure shows the information contained in the final 8 records, or about 4 seconds worth. The plane was flying along a ground azimuth of about 42 degrees and traveled a distance of about half a mile in that time. IGARI was abeam of the aircraft at the indicated time of 17:20:33.69, about a half mile to the northwest. Note that we are able to track the progress of the aircraft with the precision of a hundredth of a second. Before IGARI was abeam of the aircraft, all broadcast packets, marked here in black, encoded the correct altitude, for example, flight level 350 or 35,000 feet. For the last 2 packets broadcast after the aircraft had passed IGARI, marked here in red, the altitude encoded in the packets was 0. In fact, the position, speed, altitude, and timing of the final packet matched the final good packet in the Flight Radar 24 log. We now see that the altitude of the aircraft changed from 35,000 feet to 0 in less than a second, yet the progression in longitude and latitude was just what one would expect based on the speed and direction of travel. What on earth caused that to happen? The aircraft couldn't have actually dropped in altitude. It would have been physically impossible to do so. Further, any incident such as a fire or decompression should not have caused it to happen either, and it would have been exceedingly unlikely to have coincided with the passing of waypoint IGARI to within 500 milliseconds. Any electrical failure should have caused the transponder to cease functioning entirely, not transmit 2 packets with a 0 altitude. Even a hijacker in the electronic equipment bay or an AWACS aircraft couldn't make it happen. However, there does exist one very straightforward way to make it happen. Suppose the pilot was monitoring the active route legs page, watching for IGARI to scroll off the top of the screen. Once that happened, suppose the pilot decided to turn the transponder off. To do so, he would rotate the mode control switch, which is normally in the TA/RA position, 4 clicks to the left. Suppose one accidentally rotated the switch by only 3 clicks. What mode is that? Altitude reporting off. The transponder will broadcast a normal ADSB packet, except that the altitude will be set to 0. The pilot realized his mistake and immediately turned the switch 1 more click to the left, but it was too late. The smoking gun evidence that the transponder was being deliberately turned off had been broadcast to the world. Is there independent evidence that this is what happened? The answer is yes. When I discussed this incident with an experienced Boeing 747 pilot and asked about the meaning of the dropping of the Mode S symbol from air traffic control secondary radar, he immediately replied, "Altitude reporting off." The most plausible explanation for the disappearance of MH370 is that the pilot deliberately disabled the transponder and did so at the crossing of an FIR boundary where the action of making an aircraft disappear would be least likely to be noticed by air traffic controllers, such that the aircraft would have had the best opportunity to divert undetected. Further, the event happened just 64 seconds after the last communication between the captain and air traffic control. That is a very small window of time for a third party to have entered the cockpit and taken control of the plane. You can draw your own conclusion as to who was responsible.